Howdy everyone, and welcome back for Chapter 1, Part 2, where we'll discuss measurement and significant figures. These are some of people's favorite sections because so many times when we do online problem sets, the correct answer must have correct significant figures, and so it drives students nuts where I know I did all the math right, I know this is the right answer, but it's telling them, no, you're not right yet, something's not quite there. And it's a lot of times significant figures when it's a numerical one. So we're going to work on that today. Let's see if we can hit a few highlights there. But first we're going to talk about the metric system. All right. And that is what we use for measurements in science. We have the metric system and SI units. SI stands for International System, but because it's French, the adjective goes in the other spot, so SI units. And so the whole idea is that it's base 10, right? Everything just deals with the decimal place. The powers of 10, so 1, 10, 100, 1,000, or 0.1, 0.01, 0.001. That's what the metric system does. So it is a wonderful thing because it does make the math so much easier. A lot of people say, oh no, I don't understand it. It's just because we're out of practice or we haven't practiced enough with it. But give enough practice, you're going to find out, oh yeah, just moving that decimal on paper, not even needing a calculator to do stuff, it's going to make life a lot easier. All right, so we have the metric system going there. Well, what do we need to know? What's the key point of the metric system? The key point are the prefixes. And that the prefixes, they move the decimal. Right? So the idea of, oh, I could have this really big number, 3 million something. Oh, but if I use the prefix mega, well, then I can use 3. Right? So instead of 3 million grams, just 3 megagrams. And then the numbers are easier because people don't like to use numbers that are too big or too small. Well, here these prefixes will help us out. Right? Now, in your book, in most books, there's this huge long list of all the different prefixes. Dirty secret, we don't use most of them, at least not in general chemistry. There's plenty of prefixes. They all get used somewhere, but in chemistry, a lot of the really, really big ones or the really, really small ones, well, they're going to be in very specialty fields. When we're dealing with general chemistry, there's really only 3 prefixes that we use very commonly. There's a few that might sneak in here and there. But there's 3 that we use all the time. So that's what I'm going to focus on here. We have K for kilo, which is worth 1,000 of something. If we have no prefix, well, that's what we call the unit, right? The base unit. So that's just gram by itself, meter by itself, second by itself. And so that's just 1 of something. We have C for centi, and so that's 0.01. It's 1/100th, so 1 over 100. That's where we have, there's 100 centimeters in 1 meter. You can often remember it. There's 100 years in a century. And then the last one is lowercase m for milli. And that's 1,000 times smaller than the base unit. So there's 1,000 millimeters in a meter. There's 1,000 milligrams in a gram. All right. So honestly, those 3 will get you, say, 97% of the way through general chemistry. The others come up from time to time. We'll use nano when we talk about light in Chapter 6, where we talk about wavelengths of light. They're measured in nanometers. In Chapter 7, when they talk about the size of atoms and ions, the book might use picometers. But that's just very, very rare. These are the ones that are going to come up all the time. All right, so know these, memorize these. The next thing is with temperature. Oops. For these, we don't use Fahrenheit, so I'm not even going to put up the conversion. We just will not use Fahrenheit. The conversion you need to know is the SI unit for temperature is Kelvin. This is the absolute scale where 0 Kelvin is absolute 0. That is equal to whatever your degrees Celsius are plus 273.15. So if we have, okay, water freezes at 0 Celsius, well, that means water freezes at 273.15 Kelvin. If water boils at 100 Celsius, then water boils at 373.15 Kelvin. If we want to just reverse it real quick, degrees Celsius will be Kelvin minus 273.15. Kelvin will always be the bigger number compared to Celsius because Kelvin stops at 0, Celsius can go negative. But that's all we need for temperature. Just make sure you know those two equations. Be able to go between the two. All right, we're skipping through. All right, let's talk about sig figs. What everybody wants to. The first thing we need to know is that we have a difference between exact numbers. This is, we know them with no uncertainty. Right? Maybe you say, okay, how many people are in the room right now? For me, the answer is 1. I know that with absolute certainty. That's an exact number. Well, what's then an inexact number? This is when there's measurement involved. Not just simple counting that you know for sure, but actual measurement and estimation. Because all measurements that we do in the lab have estimation built into them. Estimation from the equipment or the method being used. There's going to be error either from the equipment or from the human using it. All these things cause it to say, no, we don't know it for absolutely sure. There's some estimation in there. There's something that makes it inexact. So when we are talking in the lab, this is where we are most of the time. So there's a few cases with exact. The main ones that we'll use that are exact are when we have an exact conversion. Just like we said with the metric system. There are 100 centimeters in 1 meter. That's exact. Exactly 100 centimeters in exactly 1 meter. But so that's the thing. By definition, it's exact. In real life, when we measure centimeters, well, it's going to be a little bit fuzzy when we get to that last decimal point, which means we don't know the last meter number either. All right. We talk about precision. I'm just going to draw a line here. Precision and accuracy. Precision is when we have multiple measurements. With small variation between them. So the idea being, maybe we've got a piece of equipment that has lots of tick marks, or maybe it's a digital equipment and it's got lots of decimal places shown that when we do the same measurement on the same object over and over, we can get the same number. Or if we need to get the same number repeatedly, and say like we're in our first lab, we're going to try to get 25 milliliters of water repeatedly. Well, which piece of equipment lets us get the closest to each other? Where it maybe not be 25, but the different measurements we do, they're all right up close next to each other. That's precision. Accuracy, on the other hand, this is the right number. All right? And so sometimes in experiments we'll say, okay, you're going to do these measurements, you're going to calculate the density of some material, but then you're going to look it up in a book and say, well, what number were we supposed to get? And so accuracy is, did I get close to the book number? Did I get what I was supposed to get? Precision is, if I do this multiple times, do I get the same number each time? And so actually it's kind of weird, but precision is more important to a chemist. We want to know that if we do the experiment repeatedly, we get the same result, even if it's wrong, if it's off from what we are supposed to get. If it's off, we can correct for it. We can say, oh, is there something wrong with this piece of equipment? Do we need to get our measurement and then add some correction factor or subtract something off? But we can adjust for that to make it accurate. But if we don't have precision, if one time we're way up here and another time we're down here, another time we're over here, we have no way to correct for it because it would be a different correction each time and we don't know which correction to go with. So precision is more important. Accuracy is lovely. All right, well, how do we show precision? How do we get that? Precision is shown by using significant figures. All right, and so significant figures, we have a couple ways we could state them. A significant figure could be all the numbers, all the digits in a measurement that were measured. Another way of saying, well, what's a significant figure is to say all the digits that are certain plus the first uncertain digit. And we say, okay, well, what does that mean? Well, when we measure, right, imagine having a ruler and it's got all the tick marks on it. And we're in centimeters because, of course, we are. Well, we have those lines so we can say, okay, if I'm measuring something, I can see that it's above the 5 but below the 6. I know the 5 for sure. It's 5 point something. So the 5 is a certain digit. But that's then going to lead us to this uncertain. That's the estimated digit. And so, I think it's closer to the 5 than it is to the 6. I'm going to say 5.3. Well, the 0.3 is the uncertain part. It's still part of our measurement, so there's our first definition. The 0.3 was measured, but it's uncertain. Maybe someone else measures the same thing, and they say, I think it's more like 5.2. Well, that's fine. We know that there's uncertainty. We know that there's estimation. So in science, you could have you and your lab mate, you could say, you know what? I'm going to write down a slightly different number from you, and that's okay. Now, it shouldn't be 5.2 versus 5.8. Those are very, very different numbers. But if you're off by one in either direction, scientifically they're the same number. And we accept that because we know it's estimated. And so, okay, when we measure, we do that. We write down what we know for sure. We estimate one spot in between the lines. Great. If you have a digital display, like on our balances, it's everything the display gives you. Even if that last number is a 0, you still write down the 0. The last number on the digital display is the estimated digit. The machine's doing it for you. All right, but what if we're given numbers? How can we figure out what is or is not significant? Well, we'll just briefly go through the rules here. So all non-zero digits are significant figures, and the SF there is our abbreviation for sig figs. And so I'll put examples here on the right-hand side when I get the rules up. Number 2 is that leading zeros are not sig figs. Zeros in between sig figs are also sig figs. Trailing zeros are sig figs, and we'll stop there. There is a fifth rule sometimes that if you put a decimal point in, it can make it sig fig. We're going to skip that rule because scientific notation will just make it easier for us. But let's go ahead. I'll give a quick example of this because this actually could be a nice test question. I'll just say, here's a number. You tell me how many sig figs are there. So if we have something like, in this case, 432 joules, well, I would say that has 3 significant figures. The 4, the 3, and the 2. They're all non-zero. They all count. Right? With this leading zeros, this means if it's something like 0.0051 millimeters, something very small. All right, well, that one, the leading zeros that are before everything else, they don't count. Only the 5 and the 1 do. That's 2 sig figs. All right, zeros that are in between. Okay, so if I have 4.05 seconds, all right, well, the 4 counts, the 5 counts, this 0 is in between, it counts 2. Well, that again is then 3 sig figs. And then trailing. Now, when we say trailing, it's not just zeros at the end. It's zeros that come after other sig figs, and they have to come after a decimal point. And so if we say something like 3.20, let's say 200 grams, that's something that you might get on your balance in lab. Well, those 2 zeros, they're after the 3 and the 2, which automatically count, and they're after that decimal, they count as well. So that one would have 4 sig figs. Now it can also happen where, I'll just give a few examples. This last rule is the one that gets people. If we have something like 40.0 grams. All right, well, say, well, what about this 0 here? Well, all you care about is this last one. It's after the 4, somewhere after it. It's after the decimal. That one counts. And now you say, oh, well, this 0 is now in between. That's like rule number 3 there. So because it's in between, now it counts. That one's also 3 sig figs. And so you could get a number that involves a lot of these. So, pause the video after I put this one up and see if you can just do a little practice problem. Say we had 0.05070 meters. Now I'm just making that up. Go ahead. How many sig figs would that have? So pause the video, count it out. Okay. All right, so welcome back. If you pause the video or if you figured it out that quick. If we go through, we'd say, okay, the 5 and the 7 definitely count. They're not 0. This one is in between, so it counts. These 2 zeros up front, well, they're leading zeros. They're in the front of the number. They don't count. So we can get rid of those. They don't count. Oh, but this 0 at the end, it's after these other sig figs. It's after the decimal. It does count. So this one would have 4 sig figs. All right. Now, question comes up, well, why don't these count? What's going on there? Or what if I had a big number, like what if it was like 50,700? How many sig figs would that be? How do we deal with that? Well, it turns out we have a special way of writing numbers in science, which is literally science writing for numbers, scientific notation. And its whole point is to let us use really big or really small numbers while showing the correct number of sig figs. It's kind of like an alternate to the metric system, where instead of using a prefix, you can use a power of 10. But usually it's we default to a power of 10 first, and then default to a prefix first, and then we'll sometimes use powers of 10 if we need to. All right, so let's do that example. Why did we say that the 0.05070, why don't these 2 count? Well, if we put this into scientific notation, right, we move the decimal over 2 spots, so it'd be 5.070, and then it would be times 10 to the negative 2. These 2 zeros that didn't count are the 10 to the minus 2. That's where they are. That's why they're not sig figs. They're not part of the number out in front here. If it was one of our sig figs, which we said this last year it was, that's why we still write it there. Okay. Now, what if we have a really big number? Like we said, if we had like 50,700. Well, this one, we know the 5 for sure. We know the 7 for sure. We know the 0 for sure. So it could be 3 sig figs. But we don't know about that 0. We don't know about that 0. There was no rule to tell us about them. So it could be 3, could be 4, could be 5. How could we say? Well, here's where scientific notation is going to save the day. Because we said, if it's significant, we include it in our scientific notation. So if it's only 3 sig figs, we would write 5.07, and and then we move that decimal, what, 1, 2, 3, 4 spots, times 10 to the fourth, that's 3 sig figs. But say this 0 here in the tens place did count. 5.070 times 10 to the fourth still. That would be 4 sig figs. Right? Or if we had 5.0700 times 10 to the fourth, this would be 5 sig figs. So if we leave it in our standard notation, there's ambiguity. We don't know how many sig figs there are. If we put it into scientific notation, all three of these numbers are worth the same amount as far as quantity, but we can see the different levels of precision. This one only has 3 sig figs. The one at the bottom has 5. Okay. Well, what do we use this for? Okay, great. When we measure things, we can make sure we include the numbers we know. We can make sure we estimate the last one. We can say how many sig figs there are. Why do we care? Well, it turns out when we combine these measurement numbers, when we do math on them, adding, subtracting, multiplying, dividing, knowing the number of sig figs or knowing where that last sig fig is in terms of place value, that determines what our final answer will be. And so the simple rules, calculations with sig figs, the number one rule is to do the math, right? So do the math like normal. Get out your calculator if you need it. Say, oh, here's two numbers, I'll add them together. Here's two numbers, I'll divide. Here's two numbers, whatever. So step number one, get your calculator answer. But then step two depends. If it's multiplying and division, then step two is you're going to change your answer to match the fewest sig figs in the inputs. All right, so whatever your two measured numbers are, you put in, say which one has the fewest. So as an example, let me just grab something here. Say we had 14.7 times, I'll keep it simple because I don't have a calculator handy, 2.0. Okay, so we multiply, well great, the 0 does nothing. So then 2, that's going to be a 4. That's going to be, what, a 9. And then that will be a 2. So yeah, 29.4. Well, hold on a second. This number that we started with, the 14.7, that has 3 sig figs. 1, 4, and 7. They're all significant. But my 2.0 input, well, that only has 2 sig figs. That means my answer is only allowed to have 2 sig figs. So I've got to look and say, okay, start with the biggest number. That's the most important. I've got the 2. I've got the 9. And then I've got to cut it off right there. And so you do check for rounding. Okay, it's 29.4. 4 rounds down. That means my final answer is 29. Even though we know, but the calculator said, but we got to go with sig figs. And so sometimes when you're multiplying or dividing, well, you get, something that gets cut off. If this happened to have been 29, say it was 14.8, so 29.6, well, then we would have rounded up to 30. And then maybe we would have said 3.0 times 10 to the first. But that's where you got to check rounding. But that's what happens with multiplying and dividing. You check the fewest sig figs, and your answer must match that number of sig figs. Same thing with dividing. Right? If, on the other hand, we are doing adding and subtracting, so add and subtract, then rule 2 is a little different. We still do the math like normal, let the calculator tell us what we got, but then what we'll do in step 2 is we will change answer so that it matches the fewest decimal places. In the inputs. Now this is not strictly correct. Really, it should be about where's the largest place value that you have your last sig fig in. But for all the problems that most books give and the tests give, the kind of giving the simplified version of match the number of decimal places works out, 99.9% of the time. So let's do an example there. Let's say we had 13.087 and we were subtracting 5.3. Well, if we do this in our calculator, we would say, okay, there's a 7, there's an 8, we're going to borrow, so that's a 7, 7.787. Okay, great. Because in elementary school, we would talk, just pretend it's a 0. But think about that. We're doing significant figures. We're saying what numbers do we know for sure, and where do we have estimated numbers? Well, if we look here, that 3 right there, that's an estimated number. I have no clue what these two numbers are. In our calculator, we pretended they were 0, but I don't know that they're 0. So do I know that these are really 8 and 7 out here? No, I can't know that. And so the rule is we're matching the fewest decimal places. This top number has 3 decimals. This bottom number only has 1. That means my answer is only allowed to have 1 decimal. Again, we check with rounding. So the calculator spits out 7.787. We're going to write down as our final answer 7.8 because that 8 will round up. So 7.8 would be our final answer there. All right, so that's what we got to do with sig figs. Now, there are sometimes more complicated setups where you might have to add numbers together and then multiply, right? A multi-step problem. In that case, the rule is you keep track of where your sig fig would be, but you don't round until the very end. Because if you, say, have a 3-step math problem, if you round each time, then the answer you get is going to kind of get rounded farther and farther away from the correct answer. So say we had to do this step and then multiply by something, we would get this number, we'd say, okay, I'm supposed to stop right here where that 7 is, but I'm going to keep the whole number in my calculator and then multiply. And then say, this is 7.77. If it's stopping here in the tenths place, this is only 2 sig figs. Okay, that's what gets applied for where should I round the multiplied answer. But we keep the whole number in to make sure that we don't round ourselves into trouble. All right. The last thing I want to talk about here for Chapter 1, Part 2 is dimensional analysis. And this is a technique that's supposed to be taught in middle schools, high schools, but sometimes I find that teachers don't call it dimensional analysis anymore, so it seems scary, or maybe the way it was taught was scary. I don't know, but we're going to try to simplify it here and say what we want. Dimensional analysis is simply converting units. All it is saying, okay, if I have this many feet, how many yards would that be? Or if I have this many feet, how many inches would it be? We can do that with height. If someone is 6 foot tall, well, then they are 72 inches tall. And so we say, okay, well, 6 and 72 are not the same number. No, but 6 feet and 72 inches are the same height. So that's the key thing. If we change our units, we'll get a different number, but it's really the same amount. We're just looking at it a little differently. And so the general setup is that you always start with your given, right? So there'll be some math problem and they'll give you some number to start with. And you're going to multiply it by a fraction. This fraction is called the conversion factor. The key is that you just take the given unit and put that on the bottom of the fraction. That way, hey, that given and that given, the units will cancel out. You put your desired unit up on top so that, that doesn't cancel out, that's what I'll end with. Then the last thing you do is put in the numbers that make this equal. It's kind of like the rule in algebra. You can do anything you want to an equation as long as it's the same on both sides, or as long as it's equal to multiplying by 1. I've got to pick what numbers make these two things equal so that I'm multiplying by 1. So you'll plug in the numbers where they go, and then you'll do the math. Anything on top, you multiply by. Anything on the bottom of the conversion factor, you divide by, and then you'll get your answer. So as a quick example, like we said, let's say we had 4.5 feet. Okay, well, hey, my given unit is feet, so I'll put feet on the bottom. Say I want inches, so okay, inches go on top. And then what makes inches and feet equal? Oh, they're equal if I have 12 inches for 1 foot. Okay, and then we do the math. It's 48. That works out to, I believe, 54 inches. All right, the feet canceled out. Now we check for sig figs. We start it with 2, 4.5. We should end with 2, 5 and 4. Okay, yeah, we're good. Now people say, well, what about this 1 here? Well, remember, exact numbers have no uncertainty, so I'll make a little note here for you. That exact conversions have infinite significant figures because there's no uncertainty, right? Sig figs are all the numbers we know and the first thing that's uncertain, but by definition there are 12 inches in 1 foot. We know that that's exact. What you need to watch out for is if you're converting between, say, metric and imperial, like pounds to kilograms or feet to meters. One of them will be 1. It might say 1 meter, but then that will equal 3 point something 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 feet. Okay, that's not exact anymore. Pay attention in the back of the book, if you have that, or there's usually a conversion thing in the back cover. That will let you know if it's exact. It'll say exact for some of those weird ones. But if you're staying within the same system, then it's usually exact. All right, so the idea there, same thing. If we have multi-step problems, we'll do this setup multiple times. You can get an answer and then put it in, or you can just chain the conversion factors one right after the other. You can convert 2 units. If you have meters per second, well, you can do one set of conversions to change the meters into something else. You can do another conversion to change the seconds into minutes or hours. So you can do all that with dimensional analysis. It's all about lining up where do the units have to be to cancel out, and then what numbers do I have to put in to make them equivalent. All right? That's going to finish up for part 2. Have a wonderful day. See you guys around.